going to do. So I had a few questions yesterday at the end regarding what I called the quantization axis, the intrinsic quantization axis of the defects. And so perhaps this will be obvious for many of you. But okay, so when I write the Hamiltonian, after if I want to do some calculation, of course, I have to use the states of for the NV centers of the S equal 1 basis, and then I need to choose a quantization axis. And usually, for instance, if I apply a magnetic field on an atom, I will of course take the direction of this magnetic field as the intrinsic quantization axis. Or another way also is perhaps to take into account the fact that I will use, like in the previous lectures, polarized light, and then it is the direction of the light that will define the quantization axis that I will use then to account for the coupling with the external fields. In our case, we are in a system where the atom is defined in the crystals. So, of course, there are intrinsic axes of these crystals, and you have to take this intrinsic axis of the crystal into account, and it is this intrinsic axis that defines the orientation of the NV centers, and also that define then how it will interact, for instance, with an applied magnetic field. So just to give you an illustration about this effect, we, of course, work with not natural diamonds. We work with artificial atoms, and basically you have two main techniques to produce these atoms. The first one was invented in the 50s by actually two groups. It's high pressure, high temperature. You know that diamond is not stable in our room temperature condition, but it's metastable. And to create that, you have to go to the stability domain of diamond, which is at high pressure, a few gigapascal, and high temperature, a few thousand of degrees. And the first one that were able to achieve that were a group in Sweden. But they were scooped by another group in the US, by General Electric, who make a public announcement, who took all the patents, and a few years after, they asked to the group leader in Sweden, why didn't they advertise and they do that? And the answer was, oh, you know, we thought we had more time. And this is always a bad idea in science to think that you have more time. Okay, so now this is really an industrial tool for producing diamond. You have this belt press, for instance. Only a few labs are equipped with such machines. They are rather dangerous to operate, as you can imagine. But nevertheless, there are a few labs which can still produce very specific diamond using these systems. For instance, in Japan, but also in Russia. And but you can purchase them, and you have usually these these yellow diamonds, and the yellow color comes from the number of nitrogen atoms that is embedded as impurities in the crystals, typically on the order of 100 part per million. So huge amount of impurities in those diamonds. And when you purchase, for instance, a cutting tool, which is said to be with diamond, it is usually such crystals that are then crushed, and you get the powder, and it is this powder that is spread onto, for instance, a knife or any cutting tool that will be said to be diamond. And the other technique that was invented also in Russia in the 60s, 70s, but it was kept secret for a very long time, is plasma, is to use plasma. So it's a completely different stability domain. Now you are at very low pressure, and you will deposit onto a substrate layers by layer a diamond. And you will build your crystal like that. So what you have here is a typical picture of a chamber. So you have this vacuum chamber. You have here the plasma glove. You fill in the chamber gases. So usually it's methane plus hydrogen the hydrogen will dissociate the methane, and then you will deposit the atoms of carbon like that, and you can build very ultra pure single crystal diamond like those ones. So this is, for instance, purchased from Element 6, but there are many labs that are able to produce such diamond. The only problem with these diamonds is that they are quite small. You don't know how to make very large diamond, and somehow it's like a problem of how you say that in English, la poule et l'œuf. The egg, and it's a kind of egg and chicken problem, because this is homoepitaxial growth, so you need to start with a diamond which is already a single crystal. So for instance, you will make those crystals here, and these could be quite large, almost quite 1 centimeter as dimension can be produced. And after, once you have that, then you will deposit on top of that non-pure diamond the layer of ultra-pure diamond, which can also be doped for instance, for high-power electronics. And the problem is that the people that are able to produce these large diamond substrates do not want to sell them. They keep that for themselves, and basically it's a kind of bottleneck for using doped diamond as a really powerful tool for high-power electronics that you might need, for instance, for electric cars or all that. So it's a kind you see about how the two techniques are linked together. This one, it's monocrystals, and this one, depending on your substrate, you can produce whatever you want. If you start from a single crystal diamond, you will make on top of that a layer of monocrystal. It's called homoepitaxial growth. But for instance, you can also put seeds, very tiny nanocrystals, a few nanometers, and then this will be the seed of the growth, and then you will have heteroepitaxial growth, and you can have nanodiamonds like that can be grown starting from these seeds. Okay, now back to this orientation axis. So if I use, you have different, of course, orientation. A diamond is a cubic crystal, so you have different orientation of these cubic crystals, which will correspond to different bonding of the crystal. And if I take, for instance, a 1,0,0 oriented growth, then suppose this is my tetrahedron of in the carbon lattice with all the sp3 bonds. Actually, it will be oriented like that. Not exactly in the axis of the growth of the diamond. And so this means that if I consider here the sample oriented like that, I have these 4 orientation equivalents somehow that can be, that the NV centers can occupy. If I take, it was observed that if I take another orientation of the diamond, 1,0,0, for instance, then you change, of course, the respective orientation of the NV, and they were able to have to change the ratio between these different orientation of the crystal. So our idea was to explore that. That was with Vincent Jacques when we together with a group in Villetaneuse, they were able to grow diamond on a 1,11 substrate. And then you have the dangling bonds, which are exactly perpendicular to the substrate. So you can imagine that now, depending on this dangling bond, you will have one carbon atom that will top on top, and then the vacancy. And it can only work in this way. So what you will have in that case is you expect that all the NV will be oriented along that. How can we prove that? So again, we have now a lot of NVs randomly dispersed in the sample, and now we simply have to check the orientation of each NV. And to do that, we use again the influence of a magnetic field. If we apply a magnetic field on this different possible orientation, we will measure the projection of the B field due to the Zeeman effect onto this axis. So this is, for instance, in that case, the magnetic field is exactly parallel to the orientation of the axis, and we can determine that this will induce a large Zeeman shift in the spin resonance spectrum. And if we now have the other orientation, we can convince ourselves that there will be equivalent, the other three possible orientation, we expect to have a smaller Zeeman shift. So now we simply have to measure that on each NV that we can find in the sample and build the statistics. And this is what we observed. We observe indeed that all the NV are oriented in the crystals compared to the other one. So they tell you that we can go quite far in the engineering of these defects by combining different approaches. Both we can do implantation, but we can also create the NV by different techniques or using this plasma-assisted growth of the diamond. Okay, so now I come back to the following of yesterday's lecture. So I will try to explain, not to go into all the detail, but at least the principles, steps that allows us to understand how the electronic structures comes from. And for many applications, you don't need that. But in some cases, you have to go back to that structure to understand it. And also, this is important to, if you want, for instance, to find other systems that would have similar properties as the one of the nitrogen vacancy centers. So the first step is to look at the symmetry. So it's like a molecular physicist approach. We look at the symmetry of the defect and the symmetry of the defect among the the different possible groups is C3V. And so we have vertical reflection and combination of rotations. And so we have this group of these symmetry groups. And then we have also, as I explained before, to build the NV centers using the dangling bonds between the neighboring carbon atoms. So that is what we need to do. And so we will construct the electronic wave function of the nitrogen vacancy from linear combination of these dangling bonds. We have 4 dangling bonds. We will linearly combine them, and that will, we hope, give us the structure. And this is the different steps. So we take now these dangling bonds. Of course, we have to write them in the good basis. So we will make a combination of these orbitals to build a set of orbitals that has the symmetry of the defect. That's the first step. And you can do that using standard group theory for using, for instance, irreducible representation. So this is what we do. This is the first step of the procedure. We have the dangling bonds, and now we build 4 combinations which will respect the symmetry of the defect. And you immediately see, so this is something which is centered on the nitrogen atom. And this is something where I will add equivalently combine the 3 dangling bonds with the 3 carbon atoms. And you have here something which is perfectly equivalent in all directions. I can also do the same now, and I will have 2 other possibilities. And you see that then, if I take into account, if I describe the probability of getting the electron in the plane perpendicular to the n-axis, I have 2 different orientations, 2 different orbitals. The one is polarized like that along the x direction, and the other one is polarized linearly, roughly, along the y direction. So I have 2 orbitals which are perpendicular to each other due to this combination of symmetry. Now, once I have that, once I have done this first step, I need now to write the Coulomb electron-nuclear interaction. So I just take the Hamiltonian, and it is now, I try to compute this Hamiltonian that I have here, the electron-nuclear interaction, into the basis of the different components. I can start, of course, with the 4 with my 4 orbitals that I defined initially, and then write the Hamiltonian. I just have a 4x4 matrix and diagonalize it. This is just brute force technique, but I won't learn much about that. So it's better to express, to define this matrix using what I have defined previously, which has the symmetry of the system. And if I do that, then I have a much simpler matrix to define, of course, to define the electron-nuclear interaction on diagonal terms plus two non-diagonal terms, and then it is not very difficult to get the eigenvalues of these systems. And then I will have also the both the eigenvalues and the eigenstate of the systems. But then I have a problem. It is quite difficult to know which will be the lowest system. So you have some kind of very general rules to order all these levels. But usually what people do is that then they go to another tool in the toolbox, which is density ab initio calculation, like using, for instance, density functional theory. And that allows you to define, to calculate the order on which all these levels will be in energy. So it's not a method that is perfect from the very beginning. At one point, you have to use other components in the description. And when you do that in the case of the NV centers, you find this ordering. So the first level is this one. It's something which is perfectly symmetric, and then the other level that will define. And you also find that this level is within the valence band of the electrons. So it's not so difficult, just a little bit, perhaps a little bit boring. So now that the ordering of states has been done, we have these systems. We have to fill these states with the electrons. So this is and just again, another point which is perhaps important. I can have pictorial representation of these orbitals. And if I come back to what I said before, you have specific properties. And this is, again, something that you can, that will be very helpful to understand the physics of the center. If I take that, for instance, this orbital, you see that there is a mean electric dipole, a static one, which is along the x-axis. And when you look at that, there is also a mean electric dipole, which is on the y-axis, perpendicular to each other. This means that these two orbitals will have a permanent electric dipole. And also, you expect that if I now look to optical transition, a little bit like what I did with in the case with my toy model for the F centers, I also expect that the electric dipole corresponding to optical transitions will be different from this transition compared to this one. In this one, it will be a linear polarization that can excite the systems and produce emission and radiation. And on the other one, that will be another dipole that will be perpendicular to the other one. So just by this very simple symmetry consideration, we already have some insight into the physics of the defect. So now I need to fill these states. So I have these 4 states, and I need to fill them with the electrons. I'm considering the negatively charged NV centers. This means that I have 5 electrons coming from the crystals, and I have a supplementary electrons, which comes, for instance, from a neighboring nitrogen impurity that gives its extra electrons to the defect. So I just write now like that, for instance, following very simply the Hund's rule. And I'm able to find the ground state electronic configuration and the excited state configuration. And so that's why you have this strange notation when you first look at that compared to the one that you learned in atomic physics. This is called E2 because you have 2 electrons on these E orbitals. And you will find that. And this one will be called A for the excited state configuration, AE, due to the fact that we have this configuration. So there is no general rule on how we write that compared to the rules that are used to build the classical, the periodic table. I have now filled the states with the electrons, so I need now to add the spin. I have 2 electrons, so I have to combine both the electron orbitals plus the spin. And then comes a big difference between what we have in atomic physics again. In atomic physics, usually we will have a large spin-orbit coupling. So I will define the state of the atom in the coupled basis, J equal L, the orbital angular momentum, plus the spin. In our case, as I will come back to that later, the spin-orbit coupling is usually very low, much lower. So we remain with a system in which the orbital part and the spin part are decoupled. And this is the trick for which we were able to consider the spin as an intrinsic degree of freedom, which is somehow completely decoupled from the behavior of the orbital electron, which will create at the same time the optical transition. So you have to think of the NV that there is on one side the electron that has this probability to both absorb and emit photons, and at the same time this electron will keep its spin as an intrinsic degree of freedom, and that spin, due to the very low spin-orbit coupling, is completely free somehow from the interaction of the orbital, and somehow will not be affected, for instance, by phonons. And this explains you why we can do very easily optical magnetic resonance in these systems compared to almost any other ones. So once I have that, I'm able then to have these electronic wave functions. I now add my 2 spins on the other side. So I have both the singlet spin state and the 2 triplet spin states by simply the addition of 2 spin 1/2. So it's very simple quantum mechanics. And now I have to write these 2 states. Again, I am not going to the coupled basis, to J equal L plus S. I'm keeping that separate. And, but nevertheless, I have to build a total wave function, which is, of course, antisymmetric in the exchange of my 2 electrons. So this means that if I have here something which is symmetric in the exchange, I have to combine it with an antisymmetric combination for the 2 spins. So it's like very simple quantum mechanics. If you have to teach something, this is a possible problem. Okay, so when I do that, again, I will find out what is associated to this combination of my orbitals, the triplet state, and the singlet state of this level. And now I have all the ingredients, I have identified the different combination that I showed on my energy level scheme, on which, if you remember, I had on one side the triplet structure associated to spin S equal 1, and on the other side, the singlet structure associated to transition that will be between states of spin S equals 0. And this is exactly what I have here. And I have the same again for the excited state configuration. Okay, so just just briefly, you don't have to of course, this is only for specialists, but I just wanted to do that just to explain you that there is no real mystery in all these states. You can really build these states from very simple quantum mechanics consideration. So now I have, again, like in an atom, the electronic part of the Hamiltonian, the spin-orbit coupling, and the spin-spin interaction between my 2 electrons. And I can also have, like I mentioned previously, the influence on strain on the defect. And the influence of strain will be, for instance, to put together closer the 2 electrons and then to increase their magnetic dipole interaction. So again, in alkali atoms, the spin-orbit interaction will have energy in the range of the terahertz, so quite strong compared to the energy levels. And that's why the total spin projection, J equal L plus S, can be optically modified, and we usually write the selection rules using this basis. In my case, the spin orbit, for the NV center, the spin orbit coupling will be much lower. And it will only split the excited orbitals by 5 gigahertz. So this means that if I am at low temperature, transition that can modify MS will be allowed. So, and then that can lead to spin photon entanglement scheme that has been, for instance, extensively studied in the group of Michel Lokin. On the other side, at room temperature, what I will have is the interactions with the phonons. As I mentioned before, remember my toy model for the Jahn-Teller effect. I explained you that in the excited state, you can have distortion of the lattice. And this is exactly what will happen. So then, in the system, the Jahn-Teller effect will be dynamical, and it will somehow average all these structures. So all these structures, all the orbitals I defined, are of course true for a rigid crystal, something that will not move. Now, if I distort that in real time and very quickly, then I will average all that. And this is what actually happens. And at the end, I have these two specific features for transition at room temperature for the NV center. The first one is, again, remember that I have my two dipole X and Y for these electronic orbitals. And then I cannot alter the spin state. They are decoupled from the spin state. So my selection rule is delta ms equals 0. I have to keep ms constant in the absorption of a photon or the emission of a photon by the selection rule. And then also, due to this dynamical Jahn-Teller effect, if I come back to my two orbitals, which are perpendicular to each other, they will be incoherent. So I will have two dipoles, but these two dipoles have incoherent emission regarding to each other. So they are actually, it's like you have two different atoms, one in like that, oriented like that, and the other oriented perpendicular to this direction. And this can be checked, for instance, very easily. If I looked to the luminescence of an NV center as a function of the incident electric polarization, and I turn the polarization, what I will have, for instance, if I take these three orientation of the crystals, I will have different absorption regarding the axis of the NV. So I will observe a sinusoidal variation of the photoluminescence when I turn the excited. I will just excite this different dipole. And now, if I have a 1-1-1 oriented dipole, I have these two now perpendicular to the NV plane. I have my two incoherent dipole. They can absorb equivalently light. And so I have something which is now becoming independent on the polarization incidence. So again, this is a very strong difference with the behavior of a single atom in vacuum. And then I can exactly apply what I did with my toy model for the F centers. Now it is just, I cannot do it so simply, so I have just to write down the orbitals. But again, I will have an excited state in which I will have a considerable modification in the spatial electron density. So this means that, again, remember the different potential curve that I wrote when I disturbed my box for confining the single electron. I will have this potential for the ground state here and the potential for the NV state as a function, for instance, of the position of the mean position of the electrons associated to the NV centers. And then I will have quantified harmonic oscillator states in these confining potential. And again, I will have, when I absorb between the absorption of a photon and its emission, I will have a strong redistribution of the nuclei that defines the NV centers. And the Franck-Condon principle then predicts that a direct transition not affected by phonons. So this is this transition here. I go from this ground state here to the ground state of the excited state without any emission or absorption of photon. So this is called the zero phonon line. Then we'll have a very small, what is called Debye-Waller factor. So either you can say a very weak absorption cross-section, like what you would expect, the 3 lambda square over 2 pi for an atom. This transition, which will be the transition that is the closest from the one of an atom, not depending on any interaction with phonons, as a very weak cross-section compared to the one that we expect for an oscillator strength of 1. And so, nevertheless, you have some signature of this zero phonon line. So this is the NV absorption that you see here as a function of wavelengths for a sample that is highly concentrated on with NV centers. So you have a peak of absorption around 550 nanometers. So if you take a green laser, you will have a strong absorption. And on the other side, we have here the bright luminescence, but very broad, because the luminescence can go onto all these levels. And then the two spectrum, absorption and luminescence, overlaps by the zero phonon line, which is specific of these negatively charged centers. So this is just how we can describe this very general emission and absorption spectrum. Okay, so in the last part of this of my talk, I would now like to talk about another defect in diamond, which is a negatively charged silicon vacancy center. So I will not go. You could apply exactly the same tricks that I wrote previously for the NV centers, but already for the NV it's boring, so adding 2 times, I guess it's very, very boring. So I will skip that and just highlight the key points why this defect is so interesting also compared to the NV. So if I take that, we can have bright single photon emission up to not 106, but 10 to the 6 counts per second. So it's typically, you get 10 times more photons from a silicon vacancy than for an NV centers. And the main feature that you see here is that even at room temperature, there is a very, very strong difference in the two luminescence spectrum. We have narrow room temperature line width. The line width at room temperature is below 1 nanometer. And a very large Debye-Waller factor. You see, as I explained in the previous slide, most of the NV emission is on the phonon side, has been modified by the emission, the relaxation of phonons in the crystals. In the case of the silicon vacancy, you have almost no phonons that are emitted. Everything is somehow, all the emission is concentrated, is funneled into the zero phonon line. And the corresponding Debye-Waller factor is almost 80%, even at room temperature. And if you go to low temperature, it becomes almost unity. Also, it has a linear polarization, but this could be very easily explained by exactly the same procedure as I mentioned. But more importantly, the defect has not exactly the same structure as the one of the NV. As I mentioned on the beginning, diamond, we usually think about diamond as a compact lattice, very hard material and a compact lattice. It's not exactly true. It has rather open space between the atoms that are bonded. And so you can easily trap an impurity as an interstitial in the crystals. And this interstitial will then bond to two vacancies. So the structure of the silicon vacancy defect that has been really proven by EPR measurement consists of one interstitial silicon atom and connected to two vacancies on the side of the crystal. So this defect has an intrinsic symmetry. And obviously, it will have a mean electric dipole, which is 0 in both the ground state and the excited state. If you compare now to the NV center, as I mentioned, has a mean electric dipole. So if there is any charge fluctuation around, that will have a strong influence on the defect. And this will be very important. On that case, I have something which, like an atom, like the 1s state of the hydrogen, has no permanent electric dipole in the ground state and also in the excited state. So if there is any charge fluctuations in the neighborhood, it won't see them. These charge fluctuations will not modify the properties of the system. And this is very important, that the intrinsic inversion symmetry of the defect makes it almost insensitive to charge noise, at least to first order. And this will result to limited spectral wandering and also to a much smaller inhomogeneous broadening of the defect. Yes?
So the silicon vacancies looks much better. So why did the...
Okay, I will try to give to explain why.
On the other ones, no?
Yeah, why not people work all on that? Okay, they are stable in nanocrystals also, due again to this symmetry. And in nanocrystals, compared to NV centers, you have almost bulk-like properties. But again, we believe, we are convinced somehow, but there's no real complete proof, experimental proof about that. There are only strong evidences that this is again due to the effect of fluctuating electric fields that modify the properties of the NV centers in nanostructures, that makes their properties of the NV very different from a nanocrystal than to a bulk. And you have, again, the same properties for all defects that can be built by combining vacancies together with group 4 atoms. So we start by silicon vacancy, we go to germanium, we go to tin, and we can go even to lead. And all these defects have been now identified. There is still some uncertainty about this defect, but you can create them. And I will explain why going down into this column of the classical table is interesting. So now if I do the low temperature spectroscopy, I usually have, in the case of the silicon vacancy center, four-line structure that are like that. And this corresponds to the splitting of the ground and excited states that, again, can be calculated exactly following the procedure I described previously. And there is a very nice theory paper. There are a lot of theory papers on those defects, but Adam Gali in Budapest has done a lot of work to compute all these structures by different techniques, especially using ab initio calculation. So again, this is the 5.5 electron volts difference between valence band and conduction band of diamond. Diamond is has a very wide band gap. And the levels are inside the structure. We have a difference of energy between the two levels of 1.682 eV, which corresponds to a 0 phonon line at 737 nanometer, so in the red. And those levels are inside the band gaps, and we know where they are approximately by, for instance, making photoconduction experiments. You ionize the system, and you see how much energy you need to do that. So you can, like that, put where these levels are inside the band gap. And now, again, due to this interaction with the lattice, we will have these two, each level will be split into two levels with different energies. So in the ground state, 50 gigahertz, and in the excited state, 250 gigahertz. And then there is, in the negatively charged state, like in the NV, you have both the silicon vacancy dot, the neutral one, and the negatively charged one. And in the negatively charged one, you have one unpaired electron, which means that you have a spin s equal 1/2. But this is the main difference with the NV centers. We cannot directly measure as easily as in the NV the spin state. So it's very nice, this defect, but unfortunately you cannot do optically detected magnetic resonance on that. So for sensing application, we miss the very convenient tool of ODMR, optically detected magnetic resonance, to measure, for instance, the influence of a magnetic field or strain on the defect. I will write that there is nevertheless a parameter that could be used to do that. So now, if I apply a magnetic field, typically 0.5 to a few Tesla, I will shift these levels by an amount which is significant compared to this difference of energy, and I have now an 8-level structure, an 8-level manifold on which I can define the different transitions. And you can do the spectroscopy of these 8-level systems and investigate where you have all the transition between these states. And so a lot of work has been done in the past years to look at both optics and spin properties. So for instance, near lifetime limited transition line widths have been observed both in bulk and nanostructures. By using two different SEV centers, people were able, this was done in Misha Lukin's group, to produce indistinguishable photons and observe, for instance, Rangu-Mandel effect. People have also realized single photon switch in nanobeam, and also, very interestingly, people have also look at the effect of what happens to these transitions when you apply a controlled strain. And the controlled strain was applied in the following way. They used a cantilever. This was a collaboration between the group of Marco Lonkar in Harvard and the group of Mete Atatürk in Cambridge, where they took a cantilever in diamond, and then they implanted silicon vacancy centered on that, and then by just bending the cantilever, they could measure how these the transitions were modified by that. And also on the spin, now if we had the spin degree of freedom, people were able to optically initialize a spin and to have an optical readout of the spin state, to have a coherent control of the spin by either microwave in the ground state like magnetic resonance, but also all optical by all optical means, playing with these different levels by using a combination of optical beams, and also to realize coherent population trapping in a three-level configuration. And this is perhaps the most interesting part, especially if you think about using these silicon vacancy centers as a possible quantum memory based on coherent population trapping and EIT. So now, if I compare the different group 4 vacancy compared to the NV centers, so this is a silicon vacancy, the germanium one, the tin one, the lead one, with different zero phonon line emission. And now if I compare to the NV, and I look, for instance, to the zero phonon line emission, it's the natural line width due to lifetime. Radiative lifetime will be something like 13 megahertz. Experimentally, we usually observed, even in clean diamond, a line shift that are more on the order of 100 megahertz to 1 gigahertz. And another problem is also that, again, this is mostly due to the fact that we will have charges, fluctuating charges in the vicinity of the defect. These fluctuating charges can modify the zero phonon line, and that will induce this kind of jitter of the line, just shift of the line due to the fact that, for instance, one electron has come and modified the orientation of the dipole, and etc. And also, now if you look to ensembles, you will have a strong inhomogeneous broadening associated to this behavior at the single NV central effect. And of course, if you increase a little bit the temperature, this effect becomes more and more important. So again, the NV center in that sense is perhaps not the best systems for quantum optics experiments, due to the fact that it is very sensitive to any perturbation that is applied on it. But on the other hand, if you want to use it for quantum sensing, you can take advantage of that effect, and so somehow there is a counterpart. And so on the other hand, you may think that the silicon vacancy is intrinsically protected for all these problems, but that also means that somehow it is quite robust in the matrix and will not be very efficient to sensing. So you cannot have somehow the best of both worlds. So to conclude, just a nice experiment that was realized in many places, but for instance in Saarbrücken and in Cambridge. In Saarbrücken in the group of Christoph Becher, and in Cambridge in the group of Mette Atatürk. So we considered in these experiments, they considered single silicon vacancy, which were produced by implantation in ultra pure sample, and then they probe the ground state spin via coherent population trapping. So they used CW laser and investigate like that a lambda scheme system in which we can connect those two states by, for instance, applying a control microwave field. And if you do the experiment, and for instance, you put this field on resonance and you scan the other field, you can observe, like in a lambda system, coherent population trapping, the atom will go into a dark state, which is the combination of those two states. And it's exactly what you see here. When you scan the two-photon detuning on this Raman transition, you observe a narrow dip at the resonance, which is the coherent population trapping in the dark state combination of this one. And if you would not have any incoherent processes between them, you expect that this CPT will be very, very narrow, will become incredibly narrow. Experimentally, what is observed is that the CPT width, line width, is actually limited by random transition due to phonons that can change the spin. And so we have phonon-induced transition, and then this phonon-induced transition between this level will induce a spin decoherence. And the spin decoherence corresponds to a typical lifetime of the CPT of about 45 nanoseconds. So if you want to use this effect, for instance, to make any kind of systems where, for instance, you want to store a photon using the CPT effect, this is not very good. It means that your storage time will be limited to that before a phonon comes and destroys it. So, and basically, the spin decoherence we scaled as a photon density square. So, again, we simply apply a Fermi-Golden rule, like what Jean-Jacques explained. And the phonon density state square as delta square, if delta is the width of the phonons and the difference, and somehow the width of this of these systems here. The electron photon scattering cross section has also a dependence on this detuning parameter on this, and there is also thermal excitation effect. You have to create the phonons by thermal excitation, so it means that you will have also a Boltzmann law for this effect. So now, is there any possibility, any strategy to improve that? You would like to improve this coherence time in order, for instance, to build an efficient quantum memory? Are there any strategies for that? And basically, you have different approaches for that, which are currently investigating. So I just describe it very quickly. The first one is, of course, as the phonon excitation probability is a Boltzmann law, a Maxwell-Boltzmann law, you want to go down to low temperature. But as 1 gigahertz is 47 millikelvin, so you need to go into a dilution fridge and to have, for instance, there were first experiments that were realized where people investigated the CPT effect by putting the silicon vacancy in a dilution fridge with an optical access. And indeed, they observed a first reduction of the phonon occupation corresponding to an improvement of the coherence time. The other possibility is to go to other system. And as you will put heavier atoms in the lattice as the impurity, not silicon, but germanium and even tin and even lead, then the ground state splitting will be increased, will be much larger. And so, for instance, if you are now at, if you consider, for instance, the tin vacancy defect, this ground state is now 850, almost 1 gigahertz, and it means that 1 gigahertz you will reduce very efficiently the system, the interaction with the phonons. But another possibility is also to use strain. Again, now if you apply strain on the system, you will increase the ground state splitting, you will enlarge the ground state splitting, and by strain engineering, you can reduce these phonon interaction that spoils the coherence times of the CPT. And this is, for instance, a very nice paper which was published last year on this effect coming from Mete-Atatürk group. And other approaches is to make a phonon engineering, so to consider these defects into a structure that will act, a nanostructure that will behave regarding to phonons like a photonic crystal. So it's a phononic crystals. And for instance, if you have a nanodiamond, a simple nanodiamond, the phonon density of state will be very different compared to a bulk. This is due to the fact that you will have a phonon confinement, and which will completely modify the phonon structures to which the system can be coupled. Another approach is then not to go to more engineered structures, like exactly a phononic structures in which you cannot have phonon propagating in that. Up to my best knowledge, this is not only theory at the moment. There have not been real evidence that this is successful. There is some first evidence. This works, but to a limited part, and this is ongoing. So you see that among that, there are a lot of works that can be done on these defects to exploit their differences from the NV centers and also their specificities, especially for making quantum memories or one photon nonlinearities or single photon nonlinearities. So just to summarize the different messages of the two lecturers. So I wanted in the first part to explain why defects, we call them atom-like systems, but nevertheless with strong differences from an atom. And always keep that in mind. And I think the behavior and the physics, the very simple physics of the F center in alkali halide is a good toy model to understand that. For the NV centers, if I now concentrate on defects in diamond, the ODMR can be performed on the NV centers. So this means that you can observe by only optical means the spin of the NV centers. And the spin of this center is very sensitive to any perturbation. So with that, you can measure many things. Magnetic field, of course, using the Zeeman effect, but also electric field, like the second order influence on the defect. Somehow you can use that to measure an electric field with nanoscale resolution. And again, if I now change the lattice in which the NV center is embedded, I will modify the spin resonance, and so I can use the NV center as a temperature sensor. There are places where you cannot easily put, for instance, a temperature sensor or usual one. So the NV will, for instance, in a nanodiamond, can be a very efficient temperature sensor for measuring, for instance, the temperature inside living cells. You take a nanodiamond, you put in that in the nanodiamond NV centers, and just by measuring the spin resonance, you can have an access to the local temperature of the system of the nanodiamond, probed by the nanodiamond inside a cell, and like that observe, for instance, the chemical processes and their dependence on that. So there are many work on that, especially for applications in biology, where people would like to use this temperature NV as temperature sensors. And of course, strain, as I mentioned. And these NV, up to now, have almost unique combination of sensitivity and spatial resolution. There are other defects which have a very strong interest, and some of you are working on that. It's, for instance, the D vacancy in silicon carbides have properties very similar to the NV centers. And the other defect in diamond, which is currently investigating by many teams, is the silicon vacancy and its derivatives. And this is more like a 3-level atoms if I compare to quantum optics. In quantum optics, you have a 2-level atoms, which is something quite boring because you cannot do much with that. But with 3-level atoms, you can do much more things, even by writing block equations. So this 3-level structure of the silicon vacancy, you can play with that, and you can somehow reproduce experiments that were done with atoms. Now, by having, for instance, microwave control, adding microwave control, all optical control, but still, people have to work on the material. And this is also something which is quite interesting in the investigation of the properties, is that somehow you link fundamental concepts with the engineering of the material, in which you can do many things, as I, for instance, mentioned with given this very simple example about the control of orientation of an NV. And especially, you would like to improve the Raman coherence in the ground state, and there are many possibilities to go on that, and that are ongoing. So thank you for your attention.
Thank you very much, Jean-François. So we have the time for 1 or 2 open questions.
It's the last lecture, so I guess you are bored. It's like the 2-level atoms, you are bored.